Okay, everybody, can you hear me without getting deaf from how loud I am? So it's my great pleasure to welcome you to, I don't know, maybe the 10th NICO lightning talks or something like that. Let's pretend that is the 10th and it's a big deal. And in that big deal, I have to give credit where credit is due. So Kellogg is putting all the other schools to shame by having half of the presenters today. So yay, Kellogg, pat yourself on the back, good job. Shame on the rest of you. So the way that we are going to be doing this is the usual, it's kind of hybrid. Oh, wrong place. We have exciting talks coming. Let's not waste time with that because you all have seen this poster. Remember that if you are on here, you can raise your hand and ask for the microphone so you can ask your questions, but we are going to keep them all to the end of the talk. So each talk is going to be 10 minutes, 1, 2, 3, 4, and then we'll have the rest of the time for discussion. So we have a very nice group of speakers that are going to tell us about their exciting research. To start, it will be Lluc Font, who's a visiting student from the University in Tarragona. So Lluc, let's welcome him.
Well, thank you. Yes, sorry. We are not sharing. Okay. Okay, thank you. Yes, I'm very excited to talk about our most recent work about information-theoretic analysis of judicial decisions to reveal socially disruptive periods and topics. So yes, I'm a PhD student and working in Tarragona with under the supervision of professors Roger Guimarà, Marta Salas Pardo, and Sergio Nazar Esnar. And for some time now, I'm visiting Professor Amaral's lab. And so the work I will present is framed in the analysis of digital documents. As we know, nowadays, all sorts of human activities like our interactions in Twitter, medical records, financial transactions, all of these human activities leave some kind of digital trace that if we know how to analyze it, we can understand better those social and cultural processes that are behind them. So in this work, we study judicial decisions, which can be seen as the trace of legal disputes. So if we understand how this, if we can measure how the content of these documents change over time, we might understand better those most disruptive issues in society. So to illustrate this general idea, we focus in a case study that that talks about, in a case study, focus on the consequences of the global financial crisis in terms of housing issues in Spain. So what we do is to take decisions from cases related to foreclosing procedures, to evictions, to squatting. And what we want to do is to measure the dynamics of the content of these cases, to measure how they change over the years, so that we can interpret these changes in terms of the social context, the legislative changes, important decisions. So all of these external factors that might have driven these changes. So with this goal in mind, we take thousands of these written decisions related to these issues I mentioned. for which we have not only the text, the written text that the judges write, but also some metadata that complement. So what we want to do with this content is to be able to quantify, because we want to be able to answer questions like, does this decision talk about this subject more than this other one? We want to make quantitative comparisons among them. So what we do is to take all the words that appear in our corpus of decisions, something that we can represent as this bipartite network, where the nodes are the decisions and the words are, and where the nodes are the decisions and the words, and a link is placed whenever a word appears in a decision. And this representation is useful because it allows us to infer a stochastic block model with which essentially finds those groups that explain better the links found in the network. And these blocks, especially the blocks of words, group together those words that are used in a similar manner by these documents. So that it means that it groups together those words that can be used in similar context. For this reason, they reveal this kind of semantic closeness, as we can see in this example. That's the reason that we can call these groups topics. So now that we know each word, what's the membership of each word to each topic, we can describe each decision as a distribution over these topics. So for instance, we can say then with this example that this decision that uses these 4 words, we could say like half the words belong to this brown topic, a quarter to this other yellow topic, and a quarter to the remaining topic. So that's the distribution of this decision, and it quantifies and it characterizes its content. Oh, sorry. Slide. So until now, this would be the regular approach when doing topic modeling of a corpus of documents, taking all the words without taking care of the order, finding the topics and describing each document as a distribution over them. But we add something else. We consider another feature in the content of decisions. We consider those citations that judges make to law. So judges cite articles in codes, in statutes, in constitutions, so to frame their decisions in the current applicable law. And we take those law articles and we perform the exact same procedure, but instead of considering words, we consider law articles. So we get groups of them, topics of them that would look like this. And we can express each decision as this additional topic distribution now using this new topic legislation topic. So having our entire corpus of decisions expressed as a collection of topic distributions, 2 of them for each decision. We aggregate these results by periods of time, taking, for instance, all the decisions that belong to a given year and computing the average distribution so that we can follow the importance of each topic over the years and measure what are the important trends, the important changes that exist. So we end up measuring with these information-theoretic metrics of divergence that I will show in a moment. So the first result I want to show is the global picture of the evolution of the importance of these topics over. So here, maybe you cannot see it, but all these layers here in 2001 represent the average topic distribution of all the decisions in 2001, where each layer is a topic and the thickness of it is the relative importance in that year. So if I extend this over the years, we can see how this picture changes, how the relative importance of topics change from one year to the next. And this gives us a global insight of where are the most important periods, where are things that are changing. For instance, this region here, we see that some topics expand, while some others might fade out, something that also happens here or here. So it gives us right away those periods where some things are going on. But we can measure more precisely these changes by computing the Kullback-Leibler divergence between consecutive topic distributions. The Kullback-Leibler divergence measures in bits how close a distribution P is to a distribution Q. And also can be thought as the conditional entropy. And when we measure it over the years, we see that in those years where we expect that things are changing more, we get higher values, like here and here. And specifically, we observe a very high value in 2016 that is present in both kinds of topics, which shows us that, those changes that occurred in the content of decisions happen in parallel for these two different facets of the content of decisions. So knowing that the global financial crisis occurred in 2007, we might wonder if we can link those changes with this event. So what we do is to look for those topics that carry the most weight in contributing to the change. So as an example of this, I show here this topic that gains a lot of importance in these years with the words clause, abusive, floor clause, interest rate. So this topic can be easily linked to two important rulings from the Spanish Supreme Court and the European Court of Justice that made statements about these clauses that are found in mortgage contracts. So what we saw here is a wave of cases that followed these rulings by incorporating where they were the statements that they made. So this example shows how we are able to interpret each topic and give some explanation for it, which allows us to interpret better our. So another way that we can calibrate our results is to compare it with some other areas of law. We took data from two very different areas of law in homicides and condominium and performed the same exact procedure. And when seeing the results for the Kullback-Leibler divergence, we see that in these recent years, we see how higher are the values in these more recent years, which gives us the magnitude of the changes we observe in our cases. So to conclude, we showed how to take advantage of the huge amount of information that comes from the digitalization of these documents. We saw how our method is able to both characterize the evolution of the discourse, the evolution of the use of words, and also the evolution of the legislation with the same methodology. Since we are using a topic model, the interpretation of the results is more easy. And this allows us to detect specific events and the impact they have in the judicial. Finally, our procedure is general enough to be applied in other judicial systems, in other courts, in other areas of law, and provide quantitative comparisons. Thank you very much.
Let's thank Lluc and quickly transition to Binglu Wang from Kellogg. And are we sharing?
Sharing?
Can you come and do that quickly? Everything becomes art in hybrid form. So Binglu, tell us about yourself.
Sure. Thanks everyone coming here. I'm Binglu Wang, currently a 30-year PhD student at Kellogg School, and it is really a great honor for me to give a presentation here about our recent research progress about the abandonment of innovation. So specifically, we'll talk about how to quantify the dynamics of innovation abandonment across various domains. In the past century, actually, the study of diffusion of innovation has been studied. The diffusion of innovation has been studied for past century, and it becomes very popular, especially after the book Diffusion of Innovation has been published. And it inspired thousands of studies from business, science to marketing. Just as how ubiquitous of diffusion of innovation, we can say abandonment of innovation everywhere. For example, the fashion and style fall out of our favor, we abandon our products, and the belief and our culture fades away with time. Research has long been interested in understanding how innovation being successful, but when and how do we abandon our innovations? The abandonment of innovation usually occurs in response to the emergence of a superior technology or in light of new information that questions its efficacy of the existing innovation. The first argument is consistent with the creative destruction theory that argues that the new innovation disrupts the existing structure, destroying the old one while establishing the new one. And the second argument supports the vacancy chain theory. That is, the old innovation somehow dead and leave the space for the new innovation to fill in. Interestingly, these two schools of thoughts offer a common property of abandonment, that is the social contagion of abandonment. For the first argument, creative destruction theory also argues that abandonment is a mirror of adoption, which usually is characterized as a preferential attachment. Intuitively understand it that we can understand the phenomena. When faced with high uncertain new alternatives, we usually turn to our neighbor or friends for some signal of their abandonment behavior as clue of the right choice. And for the second argument, the new information that questions the efficacy can be spread among social networks, which enhance the social contagion of abandonment behavior. But in contrast, there are also several empirical or theoretical work that argue that abandonment decision-making is independent, largely built on the generic or fundamental property of the abandonment behaviors. Firstly, abandonment is conscious, especially compared with other passive stops or give-ups like failure. The abandonment decision-making is an active and rational change with cost-benefit analysis. Thinking about that, when you wanted to abandon your current car or abandon your current research career, you're always thinking about the learning cost or transition cost. That's making you feel rational and you seriously consider all the options, less influenced by just the taste of others. And secondly, the abandonment decision process is informative. Because prior to the abandonment, individuals already obtained direct experience with practice about the innovation. Sometimes people more rely on their own first-hand experience, so hence making them less swayed by external factors. So given this contradictory evidence from both theoretical and empirical research, the most intuitive and the most straightforward question we want to raise concerning abandonment is, to what degree does social contagion play a role in abandonment behaviors? This question hasn't been systematically examined, largely due to the difficulty in collecting high-resolution data set capturing both abandonment behavior and social networks. Thinking about, unlike the adopting behavior like purchase, the moment when you make a decision to abandon something is less recorded. But thanks to the rapid growth of the big data, currently we have 4 large-scale data sets to capture the dynamics of abandonment. The first data set is Microsoft Academic Search. We can construct the career trajectory of each scientist, and then we can identify when scientists abandon their current research field. And secondly, we have the patent application data. So we can also trace when inventors abandon their current domains, that is when they stop applying for patent in certain technological domains. And thirdly, we have the mobile phone usage data sets. So we can trace when a user stops using their type of mobile phone. And lastly, we have the Correlated drug discovery records. So we can also trace when a pharmaceutical company stops adopting certain mechanism of actions in drug development that offer us longitudinal records of the abandonment behavior across different domains from individual to organization. And another unique feature of this data set is that it also provides us a social context, that is a social network underneath the abandonment behavior. So for the first two data sets, intuitively, we can construct the collaboration network among these authors or inventors. And for the third data set, since we have the phone call records of all users or consumers of the mobile phone, so we can build the communication network or friendship network. And for the fourth data set, we build the market similarity network among these pharmaceutical organizations to thinking about when they stop adopting some certain of mechanism of action, how they will be influenced by their neighbors. They somehow indicate the information flow among them. So by handling all this longitudinal and social network data, we firstly plot the popularity dynamics of all scientific fields. Here, each line corresponds to one scientific field, and we plot the popularity dynamics change over time. And this pattern is consistent across all four data sets. It provides one key information, that is, all curve has a rise and decline pattern, indicating the existence of abandonment. And further, we want to study what is the abandonment probability over time. And also we showed the aggregated abandoning probability of all scientific fields. We can say that there is a clear increase pattern, that is, with time goes by, the probability of abandoning field is increasing. And this pattern is consistent across all four data sets, demonstrating the powerful temporal effects. So when we go back to our core question we raised as our first research question, whether social contagion exists, that is our structural hypothesis, whether individuals' abandoning behavior would be influenced by the neighbors' abandoning decision-making. Since I just mentioned that the temporal effect is strong, so we need to narrow our focus within a small time interval to understand, to control the temporal effect. Here, I take iPhone 3GS as an example. We only narrow our focus within a 3 months time interval. And then we measure the abandonment probability of individuals as a function of number of abandonments within friends. So here we can say that when you observe more abandonments among your friend circle, the abandonment probability of you to abandon iPhone 3GS is higher. So the abandonment rate increases with the number of abandonments within friends. And we want to systematically quantify this phenomenon. So we measure the slope of this bar plot. When we plot the distribution of slope across 4 data sets, we found most slope are positive. That means in most scientific fields, technological domains, commercial products, and pharmacological techniques, the abandonment rate increases with the number of abandonments within friends. We call it preferential abandonment. So it sounds interesting because the preferential abandonment contradicts the traditional model on epidemic research and innovation substitution that suggests that abandonment should follow a Poissonia dynamics. How would this new phenomenon, preferential abandonment, impact the ecosystem? And another knowledge gap is that creative destruction theory argues that the abandonment is always beneficial to establish the new innovations. So how should we think about the existing innovations? Imagine that you are a community leader or organization top management. How to maintain your user community of the existing innovation. More specifically, how to forecast, diagnose, and handle potential hazards of existing communities. To intuitively understand this phenomenon, we first do a simulation. So we generate a scale-free networks. Here, the orange nodes is nodes in the giant component, and then the blue nodes is nodes are not in the giant component. We perform the preferential abandonment on these nodes by gradually remove nodes from this network, and remove the nodes are nodes with white. Clearly, we can say that then we trace the size of giant component change as a function of number of removed nodes. We can say that there is a clear critical point. Before the critical point, orange nodes dominates. That means there is a clear giant component on the social network. But right after the critical point, the blue nodes dominates. That means the giant component disappear. This phenomenon is interesting. Thinking about that in our context, that when you still have more than half of the user in using this innovation or adopting this technology, the giant component already disappear, and the people using this innovation are disconnected with each other. This can somehow provide us some plausible explanation of why we feel there is a sudden disappear of MySpace and Nokia. But indeed, when we check the user data, they still share a huge market. So in comparison, we do a random abandonment and capture the size of giant component in the blue curve. This is consistent with our prior knowledge that a skill-free network is robust to random failure. This finding is not trivial because when we perform the preferential abandonment and the random abandonment on ER network, two lines surprisingly collapse together. Thinking about it in skill-free networks, the preferential abandonment performs the similar way as a tag, since it removes the hub first, and which becomes a source of fragility. But in ER network, preferential abandonment, it performs exactly the same as random abandonment, which are distinguishable. So we do some mathematical formulation here to verify the percolation phenomena across different network topology by performing the preferential abandonment dynamics. The main takeaway of this study is that, firstly, preferential abandonment is universal in science and innovation. Across different domains, we have empirically supported that. And secondly, if preferential abandonment exists, it will exert different influences on networks with various degree of heterogeneity. It induces early structural collapse in robust networks with heavy tail degree distribution, and it is indistinguishable to random abandonment in homogeneous networks. In this real social world, the most networks are heavy tail, the last sentence. In real social network, most networks are heavy tail degree distribution. So we can imagine that this kind of study can help us understand better how to protect the user community and how to help with the ecosystem maintain the current structure. Thanks for the contributors.
So next from the physics department is Jorin Graham. Wow, I did not murder. Tell us about yourself.
Yeah, so my name is Jorin Graham. It's really nice to be here today. I work in the group of Adilson Motter in the physics department. And while they're setting that up, today I'm going to be talking about some of my recent research that I've done, which explores the way that the synchronization of a complex system can be affected by its surrounding environment, and in particular, how uncorrelated noise from the surrounding environment can actually enhance the synchronization of a complex system. I tried to make it. Okay, fantastic. To start off with, if any of you have ever flown to a distant place, you may have experienced jet lag. So you're tired in the middle of the day, you're hungry at night, but over the course of a few days, your body gradually adjusts to the new time zone. And the way that this happens is quite interesting. So there are a number of circadian clocks that are located throughout different parts of the body. And these different circadian clocks control different biological processes. In order for these biological processes to work together like they're supposed to, all of these clocks need to be synchronized. And the way that they achieve this is that they synchronize to a single master clock that's located in the brain. This master clock aligns itself to the local day-night cycle under the influence of light. And this is how you're able to recover from jet lag. Now, the reason I'm starting with this example is because it's a great example of the type of way that an environmental influence, such as light, can affect the synchronization of a complex system, such as the circadian system. And today we're going to be exploring how this interplay between environmental influences and internal interactions can affect the synchronization of complex systems. But to start, why do we care about synchronization in the first place? And the reason is that synchronization is a behavior that arises in a lot of different complex systems. So we just saw an example of that in the circadian system. And in that case, synchronization helped the circadian system function properly, so it was a good thing. It's important to note that synchronization is sometimes harmful as well. And an example of this comes from ecological communities. So imagine that there is an endangered animal species with only a few populations left in the world. If those populations are synchronized and one of them dies out, then the others are more likely to die out as well, which increases the risk of extinction. So these are some examples of where synchronization occurs in biological systems. It also occurs in physical systems such as power grids and in social systems such as economic cycles. And because synchronization is such an important behavior in so many systems, me and other researchers are really interested in understanding what creates synchronization and what can disrupt it. And one aspect of this is understanding how the environment influences synchronization. So a common situation that we run into is we have a complex system, and this complex system is embedded in a noisy environment. And different parts of the system are in different locations. Sorry. Okay. Okay, sorry about that. So we have a complex system that's embedded in a noisy environment, and different parts of the system are in different locations in the environment. And because of that, they experience different noise. So the noise experienced by these different parts might be quite similar if the noise in the environment is correlated, or the different parts might experience dissimilar noise if the noise in the environment is uncorrelated. And what we want to know is, how does the correlation in the environmental noise influence the synchronization in the system? And okay, what's often the case, just a second. Okay. Sorry about that. I think it's working now. So what's often the case is that correlated environmental noise enhances synchronization. And this actually makes this a lot of sense because correlation represents a sort of order. And so all this is saying is that order in the environment tends to increase order in the system. And we can see how this works in a very simple example. So here I have an example of just two populations of sheep that live on different islands, and they follow just linear dynamics. So the population size at time t just depends linearly on the population size at time t-1. Also, the islands are separated by an ocean, so there's no interactions and no coupling in the model. Finally, the sheep populations experience noise in the form of weather, which is represented by some noise terms in the model. And if the weather is similar on the two islands, then the noise is going to be correlated. If it's different on the two islands, then the noise is going to be uncorrelated. And we can just represent this using a correlation coefficient between the noise terms. And what we want to know is, how does the synchronization in the system depend on the correlation in the environment? And we can figure this out. And what we find is that as the correlation in the environment increases, the synchronization in the system increases. So correlated noise enhances synchronization in this case. And that's one way that the environment can influence synchronization. What happens is in coupled systems is that the internal interactions now modulate the influence of the environment, and this can lead to some different behavior. And an example of this was found a couple of years ago by some people in my group and some collaborators, and they were looking into what happens in networks of coupled nonlinear oscillators. And what they found is that in these coupled systems, uncorrelated noise can actually enhance synchronization better than common noise, which is opposite the behavior that we saw in the previous example. And this is also a little bit weird because what this is saying is that as the order in the environment increases, this actually leads to a decrease in the order of the system. And this unusual behavior is due to the internal interactions. So what I've been working on in my recent research is showing that this unusual behavior can occur even in simple systems. So you don't need anything like nonlinearities, you don't need oscillations. Uncorrelated noise can enhance synchronization even in linear systems with linear coupling. So let me show you very briefly how this works. So we're going to go back to the same model as previously, but now we're just going to add coupling. And the way I've represented this in the diagram is I built a bridge between the two islands so individual sheep can move from one population to the other. And in the model, this just shows up as in coupling terms. And so we'll ask the exact same question as before. How does synchronization in the system depend on correlation in the environment? And we find that now a few different behaviors are possible. So we can still see situations in which correlated noise from the environment enhances the synchronization, like when we don't have any coupling. But now we can also see a situation in which as we increase the correlation in the environment, the synchronization in the system can decrease. So uncorrelated noise enhances synchronization. And then it's also possible to see a mix of both. So I have a couple of minutes, so let me talk really briefly. 3 minutes. Okay, so let me talk really briefly about what actually causes this behavior where uncorrelated noise enhances synchronization. And to do that, I'll use an example. So what I'm showing here is I am showing the trajectories of X and Y for different initial conditions on the unit circle. And right now I don't have any noise in this diagram. The reason is that once we understand what's happening in the case without noise, that's going to give us an intuition about what's happening when we add noise. And the important thing to recognize here is that the eigenvectors of this system are not orthogonal. And this is due to the coupling. In a system without any coupling, the eigenvectors will always be orthogonal, but due to the coupling, we have non-orthogonal eigenvectors. And the result of this is that there is a region of transient growth. So usually the system would always return back to the origin, but here the magnitude of the system is able to grow transiently away from the origin before returning asymptotically back to it. And this creates some interesting dynamics. So for example, we can start from an anti-correlated initial condition. And this is going to give us information about what happens when we apply uncorrelated noise. So the system starts from an anti-correlated initial condition, and right away it experiences rapid transient growth, after which it peaks and slowly decays. But notice that as it peaks and decays, the trajectories of X and Y are correlated or synchronized. And as a result of this, when the system starts from an anti-correlated initial condition, it actually ends up being synchronized. In fact, it ends up being more synchronized than when it starts from a fully correlated initial condition. And so what we see here is that the coupling creates non-orthogonal eigenvectors, which makes transient growth possible, and that can promote the synchronization when you have uncorrelated noise, excuse me. Okay, and so, sorry. All right, let me just finish up real fast. Okay. And so this is just a very simple model. And obviously the real world is more complicated than this. Dynamics of real world systems are nonlinear. Noise in the real world is non-Gaussian and has autocorrelation. But hopefully by understanding what's happening in these simple systems, we can start to get some insight into what's happening in some real world systems. And in particular, what we saw today is that in complex systems, the internal interactions make a large difference in how the environmental influences are able to impact the synchronization. And more specifically, in complex systems, uncorrelated noise can enhance synchronization better than correlated noise. And this doesn't depend on any fancy features of the system because it happens even in very simple linear systems. So thank you for listening.
Even though we did everything we could to sabotage your presentation, you were able to fly brilliant through all of it. Thank you so much. That was great. So the last speaker today is Moh Hosseinioun. Didn't totally murder the name, or at least is kind of giving me positive feedback. And don't tell me you are even going to be able to get everything to work without. Yeah. That.
Right. Okay. Do you hear me clearly? Perfect. All right. So my name is Moh Hosseinioun. I'm a research fellow at NICO and Kellogg and a PhD candidate at UIC Business School. And I'm going to talk about skill and specifically skill value. This is a project that I've been working on with the work of great people, Ejin Yoon and Frank Nefke. So if you think about skills, we start learning them from the moment we're born. We start learning how to attract the attention of people around us, start speaking, walking, and then later how to socialize. And a lot of these skills are fundamental to what we learn throughout our lives. Imagine somebody with poor social skills, they will lose a lot of opportunities to learn from other people. Later on, we go to school where we learn a bundle of skills organized in a curriculum. Now, if you think about it, why do we need a curriculum? That's because skills are dependent on one another, and you need a curriculum to accommodate these dependencies. What I mean by that is, for instance, you need some arithmetic to learn calculus, and you need to know calculus before you learn physics. Now, what I'm trying to show with this example is, as you need progression in calculus, or as you need progression in physics, you need to come back and obtain a more sophisticated understanding of its prerequisites. So let's call this, for clarity, vertical interdependence between skills, because we're looking at layers of skills, the most fundamental to higher level skills. Now, this is not the only type of interdependence between skills. Another form happens when you're performing job tasks. You often need more than one skill. For instance, if you're teaching chemistry, you need to communicate well. You need to organize information. You need to have some context information about chemistry, not to mention infinite source of patience to deal with students. So let's call this horizontal, because horizontal dependence between skills, because you have to have multiple skills present at the same time to perform a task. Now, why do we even have dependence between skills? It arises from specialization and task complexity. As you have more complexity of tasks, you have to divide work between people. And as you have more specialization and you increase the depth of our knowledge, we have come to face more complexity. So as we get a more depth of knowledge, the distance, the chain of dependence at the vertical level increases. You need more time before you go from a novice to an expert. And as you have a more complex environment to deal with, you need more and more skills to be able to handle that. Now, the question is whether we can observe this. And well, the dilemma is, since we have limited attention and limited efforts, how do we increase our value as workers, given that these are very complicated situations to gain skills? So there are two ways that we can think about a value of a skill. So it depends on how good you are in a skill. Nobody's going to pay me a dime because I think I'm a good chef. And at the same time, it depends on what sort of skill you have. So some skills take investment. They need education, experience, and efforts, while others might not. So if you think about it, the more investment you have, the more effort you put into your skills, intuitively would lead to more value. Now, the question is, do we observe this in the real data? What we do in this work is we try to distinguish between skills observed in the US economy. We try to distinguish between the fundamental and the higher level skills. And then we really focus on the vertical interdependence between skills. We focus on that type of interdependence because it facilitates the horizontal interdependence that we talked about. They also are a very good source of information about how much investment you put into your skills. And then finally, we try to relate the vertical interdependence into skill value. Okay, so let's say I take one skill, arithmetic, and I go over the US economy and I ask each occupation, how intensely do you use this skill, right? And I created distribution, a histogram of these usage intensity and the number of occupation for each level of usage intensity. Now, for a fundamental skill, you would expect that most occupations use them a lot, or the skill is very relevant to them. So you get a left skewed distribution. Now, in contrast, for a specialized skill, you would get few occupations that use this skill very intensely, but most occupations don't really care about the skill. So we have this conceptual definition, and we take it and apply it to representative survey of the data on US labor skills, where we have about 1,000 occupations and 120 skills. And for each of these 120 skills, we formed the same distribution, and we compared it and the similarity of the distributional shapes, running clustering, and then we uncover 3 stylized forms of skills. On the left, we have these general skills, which manifest left skewed distributions. These are the lowest level, the most fundamental levels of skills. Examples that come out of our data, for instance, are oral expression, critical thinking. These are intuitive. On the other extreme, we have specific skills. These are the higher level skills that manifest the right skewed distribution. Examples which are interesting, I think, are programming and spatial orientation. We have in the middle those skills that are relatively balanced. Examples are mathematical reasoning and negotiation. We call these common skills. So now, the question is, if I look at the specific skills that are the higher level, right? If I look at them, do I see similar patterns of interdependencies, dependencies across the vertical levels on these lower level skills or not? To answer that question, we form a skill co-occurrence network where each node is a skill, and there is an edge between 2 nodes, 2 skills, if there is a significant amount of co-occurrence at the occupational level between those pairs of skills. Each node is size-based proportional to the education, and the color follows the clustering that I just showed you. So red nodes are fundamental general skills. Green are intermediary or common skills, and the blue ones are the most higher level and specific skills. Now, looking at this figure, the first thing that pops up is you have 2 clusters. So on the right cluster, you see most of the general skills are residing in there, and then they're surrounded by common and specific skills. You can also notice that the size of the nodes are bigger, meaning that these skills are associated with more education. The other clustering, however, you see no general skills, but you see a bunch of common and specific skills. So intuitively, in this cluster, you have specific skills that are dependent on general skills. You have very strong vertical dependencies, versus this one, you have skills that are essentially flat. So I have a cluster of skills with strong vertical interdependence, one with weak interdependence. Now, the question is, can I find anything about value of these skills? Oh, before that, let me also show you some examples. So for instance, here, we see critical thinking is a skill that shows up in this cluster, relatively closely positioned to mathematical reasoning and to programming, meaning that these skills are quite dependent on one another. The other cluster, for instance, an example that pops up is spatial orientation. So very intuitively, you can see that these are skills that are quite physical. These are quite cognitive skills. Now, looking at, let me also just explain them here. So I'm really interested in comparing skills that are close to the general skills, specific and common skills close to the general skills, which have very high dependence, vertical dependence, against these, and see which ones are giving me higher values. So we split skills specific and common based on how close they are to the general skills or if they are far from the general skills. Okay, and then to get a sense of their value, I look at occupations and measure their usage of each subset of skills. So each point in any of these panels is an occupation. And along the x-axis, I'm measuring the average usage of each subset of skills. For instance, specific skills that are close to general skills, very high vertical dependence. What we see here with the slope of the lines is that those skills, both specific and common, that depend on general skills, which manifest high vertical interdependence, are associated with increase in wages versus the other clusters not. More interestingly, if you look at just the usage of general skills by occupations, you can get a really good prediction of their wages. Now, this is not to say that if you have a general skill, you can automatically become very productive and gain good wages, but it shows you that it predicts well what skills you are able to accumulate over time and then are able to gain good value out of it. So I want to conclude by pointing the importance of general skills as skills that unlock pathways to creation of value. And this is important because contrary to the common sense and most of the scholarly work, which have largely neglected general skills because they're used by most occupations, they're actually very important for policy. Because if you're trying to counter job displacement, you can't go around teach people specific skills. You have to actually teach them general skills and that which allows them to go on and learn the skills that they can gain value. All right. Thank you for your attention. Would be glad to take questions or have your feedback.
I want to give a chance first to questions from inside the room. And Andy, do you know if we have any questions from the...
Thanks, Brian.
Yeah, seriously.
So
Go ahead.
my question is for Binglu. So, I mean, you mentioned this example of like iPhone 3G, right? I don't understand why abandonment is not just the inverse of adoption. So like iPhone 3G that, you showed that histogram. What about iPhone 4 or whatever? Like, won't it be just like the inverse of that histogram?
Other questions? I actually have a question for Moh. Fascinating presentation. Maybe I'm drawing a conclusion from an N of 1, which was the example of something that was specialized and it was not part of this vertical thing, which was spatial orientation or something like that. And I was wondering if that is representative of other types of skills that we actually do not do a good job teaching. That is, when we think about basic schooling, we teach people how to read, how to do arithmetic and stuff like that. but there are a bunch of other skills that we actually don't take care of teaching properly in school. We don't teach kind of physical ability or orientation or art in a sense. Am I extrapolating incorrectly for one, or do you have some more examples of that kind?
This is a very interesting question. So there is one component of it, which is teaching a skill. One is which skills are being used together in a job. And these are definitely related, right? The data set we used and the way we looked at it is what are the necessities for people to be able to do jobs, right? And what we see is jobs are divided in that way. And maybe that also comes from the fact that certain skills are not being taught in school. Let's say you don't teach spatial orientation to a math major, right? Not at least directly. So what we see, the skills are bundled are, let's label them as the literature has. Cognitive skills are in that left cluster where you had general skills and you observed strong vertical interdependence, versus the physical ones, spatial orientation, finger dexterity, and a lot of other physical skills are roughly not being dependent on other things, versus basically the way we draw the conclusion that essentially you can learn these skills at the same time in parallel without having to have very strong prerequisites, at least at the level of division that we have for skills.
So if I think about the skills that you are talking as having a vertical structure, I would think about skills that are related to the administrative state, to the bureaucracy, right? Kind of keeping track of things, making records, integrating data and stuff. There are other things that are extremely useful, like orientation, right? I don't like to get lost. And you could think the reason why we don't teach people how to orient ourselves is because we don't know how, or we don't care, right? And there are things, for instance, about memory that it's actually, you can figure out that it's about don't care, right? So there were studies about people like the London cab drivers, right? That have this amazing development of their orientation skills, of memorizing stuff. And we know that we can teach stuff about memorization, right? The memory palaces and things like that. So there are strategies in which we could be teaching them, but somehow they have not been valued or pushed in a certain way. And I was wondering to what extent this is also telling us about what current societies value and whether some of those are things that should be more or less valued. I don't know.
I think that you're absolutely right. I think from a societal perspective, and to take a step back and think about values and what we need to value, you're absolutely right. Our data does not put me in a position to tell anything about that, but I think it's absolutely right. There are skills that I think would be very valuable to invest in and to bring them into the curriculum. But I also want to be mindful about what I see in the data, which is that most occupations are very limited. So you see skills have very different distributions. We don't observe that for occupation. Even doctors, CEOs, these are high-paid jobs. And our initial thought was, okay, these are going to be very high skilled in the way that, as the language goes, these are high skilled compared to, let's say, cab drivers or models. But what we observe is that actually there's not much variation in terms of how much skills, in terms of the extent that skills are being learned by occupations, but it's more about the distribution and what skills are being bundled and what skills are being learned together that allows occupations to create differentials in terms of wage.
Come on, people, shame on you. Oh, I think I'm going to select someone at random to just ask a question. Why don't you ask a question? And I'm walking slowly to give you time to think about one.
Hello, everyone. This is a very new field for me. That's why I don't understand many things. Maybe I have a lot of questions, but that are the basics. One of the most interesting part for me is the desynchronization. And have you tried to work with a more complex model instead of using just this differential equation linear?
Yeah. Excellent question. See, it's not so hard. They did an extraordinarily good job. Excellent question.
Yeah, that is a really good question. I have to agree. So the reason we work with simple models is to try to actually get rid of the extra complications that aren't necessarily contributing to the effect. So I would say that the goal of my research was to show that this effect could actually happen in very simple models, that it didn't actually depend a lot on the detail of like the dynamics or something. But so now one of the next things we want to do is, can we maybe find some data to support that this type of effect actually happens in a real world system? It's not just to prove that, it's actually something real and not just, something that only happens in simple complex systems.
So it's after 1 o'clock, so I'm not going to torture you anymore, but I just want, and I'm not going to do this ever again. Actually, I'm lying. I probably will do it again. But, just ask questions. If it's something that you don't understand, ask about it. Sometimes the most simple, naive questions are the best ones. So, feel like participating. It's good for you, and it's good for the speakers to kind of see that you tried. Okay, so thank you so much for being here and participating, and let's thank all of our extraordinarily good speakers that survived even sabotage.